this problem occurs when we are looking at acids and bases. What we have done so far is we have spoken about what is generally known as strong acids. And also strong bases. Now, these strong acids are really defined by basically saying a strong acid, if you've got, for example, hydrochloric acid, and you put that in water, it will almost completely break down into protons and chloride ions. And we said this one here is the acid. And the chloride, what is that? Bless you. It is the corresponding base, exactly. So that's the base. And that is a conjugate acid-base pair. And just as a rule of thumb, you can think of conjugate base pair, the base differs only by one proton. Or the acid has one proton more than the base. That's a conjugate base pair. Now, unfortunately, life isn't that simple. I hate to tell you that. Because in biology, in the cell, we hardly ever encounter strong acids. There's only one place, obviously, in the body that has a strong acid, which is the stomach, which produces HCl. All the other acids in our body are weak. Luckily, I have to say. Just to give you an example of a weak acid in your body, what I want you to do is, for a moment, stand up. And now, what I want you to do is ski training. If we don't know how many protons we have, we can't calculate the pH, can we? Let me give you an example. Let's say we have HX, and we start with, let's make it easy, 1 mole per liter. And this guy disintegrates H plus X minus, and it is an equilibrium. And we know that, bless you, that 10% will dissociate. Will dissociate. Yeah? So when we wait long enough, then everything has sorted itself out. And we will talk a little bit about this situation when we speak about equilibrium. But what will happen? I start with 1 mole per liter, and then I wait. So this 1 mole per liter that I have at the beginning, 10% of that will disintegrate. So in my mixture, how many protons will I have left? Or will I have produced, I should say? 10% of 1 mole? 0.1. So I have 0.1 mole per liter. Yeah, that is what I have produced. How much of the X minus have I produced? Of the X minus? 0.1. mole per liter. Exactly. Why? Because for each proton that I generate, I also generate an X minus. Make sense? How much of the Hx do I have left? Somebody said 0.8? 0.9. Why is it 0.9? Why is it 0.9? Why is it not 0.8? Exactly. So what you do is you basically split this guy here in two. Yeah? And for each one of those, of the Hx, you produce 2 bits here. But it's only one part here. So therefore, you have 0.1 mole per liter of the protons, 0.1 mole, the same amount, of the base, and you have left 0.9 mole of what you originally had. Yeah? Okay, now we could very easily calculate our pH from that. Because we know that we have 0.1 mole per liter. We can do pH. pH equals minus log of the proton concentration, and so on and so forth. Yeah? Now, we can write this, actually, as a sort of an equilibrium. We can write, and let me write this down again, Hx gives us H plus X minus. We can write this as an equilibrium. And an equilibrium we always write in a way that we have the products on top divided by the reactants. So this would look like H plus times X minus, that's the concentration, divided by Hx. And to indicate that we are already looking at it when it has established itself as a sort of an equilibrium, whatever this is, we sometimes put ek in here. And this, actually, this fraction is a constant. And it's frequently expressed as an equilibrium constant. Okay? And you can basically do that for any kind of reaction that you want to look at. So, for example, A plus B gives C plus D. You can say, okay, the equilibrium constant for that is C times D divided by A times B. That's a general equilibrium, and that is how you can describe it. This equilibrium up here, this guy, this equation here, because it contains an acid. Because it contains an acid, this equilibrium constant is also very often written as Ka. And some people call that the dissociation constant of the acid. Yeah? So far, pretty boring, not terribly exciting. What I want you to do now is, can you please write down on a piece of paper the equilibrium equation for this reaction? X minus plus H2O. What do you think will happen in this reaction? Any ideas what could happen? Be creative. What will happen? Loud over there. Any suggestion is good. We will get OH minus. Yes, that's a very good suggestion. And what else? We would get plus HX. The X will try to claw, to steal one of the protons from the water. Yeah? So what I want you to do now, 2 minutes, is write down the equilibrium equation for this guy. Please. And you can, discuss that amongst yourself. So, for me, it would be, let's write down, K, equilibrium, that's the constant, equals. What do we have on top? We have OH minus times HX, right? Divided by X minus times H2O. Do you get that? Yeah? No? The H, sorry? Say again loud. Yes. What you do is you write this side on top and this side at the bottom. Yeah? Sorry, what was the? Somebody complained about the H2O. This is, as it is written, absolutely correctly, I have to say. But usually we do everything in water anyway, so very often people just simply ignore that bit here. And they say, well, we put it in here. So what people usually do is they do a little bit like, dirty tricks. And they incorporate the concentration of the water in the equilibrium constant. We can do it, and usually it is done, but let's not worry too much about that. Yeah? Now, again, this one here is a very special stuff because we have got an OH in it, an OH minus. What is OH minus? Acid or base? So this, again, like with the Ka, it has a special name, this equilibrium constant. What would you suggest? K? Kb for base. because chemists are incredibly imaginative people. Yeah? So what we've done is we just simply expressed these things as Ka and Kb, these reactions. And that actually works for whatever we are looking at, whatever reaction we are looking at. Now, let's see what we can do with that. For example, we have our HCl. H plus Cl minus. And we can write this as Ka equals proton times chloride divided by HCl. Now let's see roughly what number this Ka tells us, or what number this Ka gives us. Let's say we start with, say, 1 molar. Yeah? And everything dissociates of this 1 molar. So, in our equilibrium, once we've waited a little bit, how many protons have we got? 1 molar. How many chlorides do we have? 1 molar. How many HCl have we got? Huh? 1 molar? How many HCl have we got? None. Because it's all gone. It's all converted into H plus and Cl minus. There's no HCl left. Can you please do that on your calculator? 1 times 1 divided by 0. It's what? No? What do you mean no? Can't do it. 0. Oh, you can't do it. What you do is you divide something by something very, very small, don't you? You divide 1 by something extremely small, very, very small. What does 1 divided by something very, very small give you? Something big, something small? 1 divided by something very, very small. Something very, very big. Very, very big. And in fact, if you did 1 divided by 0, this would give you infinity. Yeah? So, in the case of our hydrochloric acid, this Ka would be very, very big. That I indicated like that. Now, let's go back to our Hx. Hx gives us H plus X minus. Ka in this case would give you H plus times X minus divided by Hx. And we said earlier, we start with, say, what did we say? 1 molar, we start with that, and then only 10% dissociate. We said we have 0.1 molar, 0.1 molar, and then we have 0.9 molar of this guy, of the Hx. So let's put that in. We have 0.1 times 0.1 divided by 0.9. Can you do that? 0.1 times 0.1 divided by 0.9. What does that give us? Anyone? What did you get? 0.01. 0.01. Did you get that? Yeah? 0.01. Our Ka is pretty small. Yeah? Okay, let's say we have Hy, wait a moment, we have Hy, it's another acid, dissociates into H plus and Y minus. Let's say this is lactic acid. Again, we start with 1 molar, but now it's not 10%, now it's 1% that only dissociates. Only 1% of the whole stuff dissociates. How much of the protons do we produce? 0.01 molar of the proteins, exactly. How much of the Y minus? The same, 0.01 molar. How much of the Hy have we got left? 0.99 molar, exactly. So this is a fairly weak acid because it really does not want to disintegrate. Can we calculate from that the Ka? Ka equals proton times Y divided by Hy. Yeah? Or, put some numbers in. Ka equals 0.01 molar times 0.01 molar divided by 0.99 molar. And you get 1 times 10 to the minus 4. So our Ka is even smaller than the previous one. The previous one was 0.01. Now, the Ka for this weaker acid is 1 times 10 to the minus 4. Can we sort of come up with an idea of how this Ka tells us something about the acid? We said strong acid, Ka is high or low? Very high. Ka is high. Weak acid, Ka is low. Or I should probably say small. So a high Ka indicates a strong acid. A small Ka indicates a very weak acid. Yeah? Now, unfortunately, as you probably have noticed, biochemists and chemists and biomedical scientists and biologists and all the other clever people, they hate working with 1 times 10 to the minus 4, 1 times 10 to the minus 7, things like that. They hate that. Remember pH? They didn't like 1 times 10 to the minus 7 molar. So what did they do? Say loud. They took the minus log. So pH, we said, equals minus log of the proton concentration. And they do exactly the same here with the Kas. And what they do is they take what is called the pKa equals minus log of the Ka. Let's see what the consequence is. Let's say we have a Ka of 10. And we have a Ka of 0.1. Which one is the strong acid? Which one? The 10. That's the strong acid. And obviously the 0.1, that's the weak acid, isn't it? Now what is the pKa for the strong acid? The pKa, so pKa equals minus log Ka. So here the pKa is minus 1. Yeah? What is the pKa for the weak acid? 1. So it does exactly the opposite to what the Ka does. Weak acid, you have a low Ka, but you have a high pKa. I give you 2 pKa's. pKa1 is 4.75. pKa2 is 6.8. Which one is the stronger acid? Which one is the stronger acid? The first one? Why? You are absolutely right. The stronger acid is this one. Because the pKa is lower, that means the Ka is higher. So this is stronger, this is weaker. Does that make sense? And for each acid, you can actually come up and you can identify, under certain conditions, a pKa. This tells you how strong the acid actually is. Low pKa, strong acid. High pKa, weak acid. Okay, now we said we can write, let's do this example again. We have Hx gives us H plus X minus. And we said we can write an equation for that. We can write Ka equals H plus times X minus divided by Hx. Okay? Now, I solve this equation. For H plus. Because I want to do a pH. I want to calculate the pH. So what I do is I just simply bring this to that, and this goes down here, and I get Ka times Hx divided by X minus equals H plus. Yeah, I just rearrange this. Does that make sense? Yeah? Are you happy with that? Just took that down here, and this goes up here, so I've got Ka times Hx divided by X minus. What did we say about pH? What was the pH defined as? pH, there was something, pH equals minus log of H plus, wasn't it? Remember, vaguely? Well, we can calculate our H plus concentration. Can we now calculate the pH concentration? Well, actually, I think we can. All we need to do is really, we take both sides minus log. What have we got then on the left-hand side? We have minus log of Ka times Hx divided by X minus equals minus log H plus, right? Both sides minus log. What is minus log H plus? That's pH. Our pH equals minus log Ka of this thing here. Actually, we can do even better. What we can do is we can try, I'm running out of space here, minus log Ka Hx divided by X equals pH. This is a real mouthful. Nobody can remember that. But what we can do is we can get this minus log, we can sort out this thing, what's in this bracket here. How can we do that? Well, we can write it as minus log Ka minus log Hx divided by x minus. And that is still the pH. Okay? Are you with me so far? It's not essential that you need to know how we get to this. But it's quite nice, because you can do that as a sort of a party trick. I would like to know to which parties you are going in this case. It's the Big Bang party. What did we say for minus log Ka? What was that? Loud? pKa. So we have pKa minus log of Hx divided by x minus equals pH. It's a funny thing, this thing. Let me write it again on a new page. pH equals pKa pKa minus log Hx over x minus, or pKa minus log Hx, we said that was the concentration of our acid divided by the concentration of the base. Who gives a damn? Well, actually, this equation allows us to calculate the pH of a solution as long as we have the pKa of that, and as long as we know what the ratio of acid to base is. So, doesn't make even more sense now. Why would we want to do that? Actually, this equation is one of the fundamental equations in biology. This equation is so fundamental that it even has a name. It is the very well-loved Henderson-Hasselbalch equation. Please don't say Hasselblad equation, because Hasselblad, that is a world-famous maker of cameras. Has nothing to do with that. This equation actually describes the pH that is going on in, for example, your blood, in your cell. And it describes actually a phenomenon that is called a buffer. When you did this exercise, you produced lactic acid. You produce quite a lot of lactic acid. This lactic acid goes into your blood. However, if acid goes into your blood, it will kill you. A very cruel way to die is inject yourself with 100 milliliter of hydrochloric acid. It's not good. It's bloody painful. So if you have an X, I'm not saying anything now, right? You don't want to do that. But why does the lactic acid from your muscle have no effect on your overall well-being? Because the blood has a fantastic way to eliminate this acid. And it does so with what is called a buffer. You have certain diseases that do produce acid. Anyone hazard a guess what one of the very common diseases is that produces an acid? Loud? Diabetes. Exactly. Diabetes is a disease, is a metabolic disease that produces lots and lots of acid. So, by law, people with diabetes should die. They should be dead. They can't survive. There's so much acid in the blood, theoretically, that they shouldn't be around. If they are not around, they can't have offspring, and diabetes would have, be eliminated a long time ago. But the blood has a way of dealing with this acid. And it can eliminate the acid. It can sort of neutralize the acid. It can buffer the acid. And what a buffer does, a buffer actually is meant to resist a change in pH. How it does that, I show you on Monday. Have a nice weekend, and for those of you who do the chemistry,